All right, so let's kind of talk through just a little bit of 6 and 7 to kind of get on the right track. And so for 6, I have the intersection of all n and n of 0 to 1 over n. Okay, so first let's just get the notation right. When you have something like this, what I would recommend is to just write out a couple of things that we're intersecting to kind of get a feel for it. So I'm just going to start with n equals 1 and write 0, 1, intersect 0, 1 half, intersect 0, 1/3, intersect dot, dot, dot. Are you okay with going from big intersect notation to this kind of feel notation? Okay, so let's talk through why we do that, right? So we're thinking of this n. These are my indices. So I'm just thinking, okay, natural numbers. That's 1, 2, 3, 4, dot, dot, dot. And so then I put in the first n. N is 1. It gives me this one. Then I put in 2 to get the next one, and 3 to get the next one, and so forth.
Yeah, I guess, like, I'm okay with, like, in this example.
Okay.
But, like, on the practice exam, I was, like, very confused.
You just have to, like, I think it's really helpful to just start writing out examples.
Okay.
Like, it was talking about, like, yeah, like, n minus this weird intersection, like, say, okay.
Because
Like,
that was, like, a set that, like,
right.
this is more like, these are, like, pairs.
Well, okay, so what kind of notation am I using here? That was going to be my next question. So this is like an interval notation.
Yeah.
So this is the set of x that goes between 0 and 1, including the endpoints, because I have the square brackets and not the parentheses. So before, yeah, on the practice exam, it was different sets. But if you think about, like, subtracting off a union, I have to subtract off all of them. So I can first subtract off all of the things in my first set, and then all of the things in my second set, and so forth. Like, if I have, like, all of these numbers, and I have bags of numbers, and each of these I'm subtracting from my set.
Okay.
And I need to subtract, like, the whole union of all of these bags. But I can go ahead and just subtract the first bag first, and then the second, and then the third. And so if you think about it in that way, to kind of give yourself some examples, it's helpful to think through. So I feel like being comfortable enough with intersections and unions to kind of think about what they're doing, so that then you can think about them in different perspectives can be helpful. So here, let's picture it. I'm taking the interval 0 to 1 on my number line, and then intersecting it with 0 to 1 half,
Okay.
and then 0 to 1/3, and 0 to 1/4, and 0 to 1/5, and 0 to 1/6, and so forth. So what's going to be left when I'm done intersecting that?
0.
Just 0. So conjecture, this is equal to just the set that only has 0 in it. How would I prove that?
Just, does the natural numbers go to infinity?
The natural numbers do go to infinity, but I can't use infinity because infinity is not a number, right? There was a proof just like this where everyone was like,
That's what I wrote.
oh, the sets are getting smaller and smaller each time, so we know that they're going to be empty at the end. And I was like, well, they're not getting smaller and smaller because they're still infinitely large each time. So let's do a contradiction. To show that this is only 0, let me explain why nothing else could be in there. And that's kind of what the good way to do that homework question was. To show that that was the empty set, you need to explain why each individual element couldn't be a member of that set. So let's say, zoom nuts, there exists some x not equal to 0 such that x is in the intersection of all of these. I want to proceed by cases. Can anyone think about what my cases might be? What types of numbers could you think maybe might be an x? Or definitely not an x? -3. Is -3 in there? No, why not? Well, no, because remember the natural numbers are just the indices down here. This
Oh.
interval notation always means real numbers.
Okay.
But at most, what kind of real numbers does it have? Positive ones. And right, really, the first set only went from 0 to 1, right? So, like, note if x is less than 0, then x is not an element of just that first set. So x can't be in the intersection. So I can conclude that x has to be at least, so x must be greater than 0, because I assumed that it was not equal to 0, and now I explained why it couldn't be negative, so now it must be positive. And so, okay, it's a positive number. Why can't it be in this set? Do I want to think of really big positive numbers not being in the set? Like, what's got like the best chance of being in the set? A really big number or a really small number?
A really small one.
A really small number has the best chance of being in the set. Because, like, I know that it can't be bigger than 1 because it wouldn't be in the first set. It can't be bigger than a half because it wouldn't be in the second set. It can't be bigger than a third because it can't be in the third set, and so forth. So I'm thinking of, like, okay, I've got this little tiny number, and I got to figure out why that can't be in this set. So that's a little hard. I can say, you know, so consider 1 over x. Now I'm thinking of x as this tiny little number, and so 1 over x will be kind of a big number. Is it the biggest number in the world? No. Is there a number that's definitely bigger than it? Right, because numbers are infinitely large. So there exists some number in the natural numbers such that 1 over x is less than n, because the integers are unbounded. But that means that x, now I know this is a non-zero positive number, so I can do all sorts of things I want to do in inequalities. So I can say that, like, you know, 1 is less than x times n, or 1 over n. What did I do? Is less than x. I'm bad. I bad mathed. Oh, good. Wait, that's fine. No.
I think that makes sense. There has to be a number where x is greater than.
But x being bigger than 1 over n isn't what I want. I wanted x less than 1 over n. I should have done my scratch work. So I was trying to show for every x, there's always an n such that x is less than, oh, no. This is what I wanted. I wanted to show that x was not an element of 0 to 1 over that n, i.e. x was bigger than 1 over n, which is what we showed. So we can always find one that's smaller than it that doesn't have it. Okay, so since x is bigger than that 1 over n, x is not an element of the set from 0 to 1 over n, so then x would not be an element of the empty set. Of the intersection of those. So for anything that's not 0, it can't be in the intersection. So the only thing that could be in the intersection is 0. And so that's how we show that. That's definitely a toughie. That's like an A+ problem, bonus problem level. But it's good to start thinking about how to unpack those definitions. That's what I wanted you to get at.
But like
Think
this won't
about.
just be like a question on the
No, this is like a think about unpacking what these definitions means types of question to kind of get used to that. And yeah, for 7, let's put 7 into words. So I can put this like this. For 7 here, it says if intersection A in I AA equals union A in I AA, what can you say about the collection of the AAs where A's in I? Right, like it looks really gross, but the whole point is I want you to be able to see something gross like this and make sense of it. That's what this question is doing. So what do I want to think about? I got a bunch of different sets, A sub whatever, A1, A2, A3, and then I'm intersecting them, but I'm also unioning them, and those things are equal. What does that tell me about the sets? So we start thinking, how does the intersection usually compare to the union?
They're not the same.
They're usually not the same. Which one's usually smaller?
The intersection.
The intersection. So the intersection's usually smaller. And now we're saying that the intersection is actually equal to the union. So what has to be true about these sets for the intersection to have to equal the union?
They're equal.
They have to be the same sets, because if anyone had any extra element, that element would be in the union, but it wouldn't be in the intersection. Right? So the point of the questions like that is that to make you be willing to read the symbols enough to figure out what it's actually saying, so that then you can answer the question being like, oh, they must be equal to each other. Because if they weren't, there would be an extra thing in the union that wasn't in the intersection.
I'm gonna be so crazy whispering to myself.
That's fine. Just don't whisper to anybody else.
Just me.
All right, are you ready to disperse? Have a weekend of fun?